flip a light switch, charge your phone, or tune into a radio station, something invisible is happening behind the scenes.
Electromagnetic induction, the invisible force that runs the world. Welcome to the plan. I'm your director for today, and together with my team of engineers, we're going to show you exactly how magnetic induction works inside alternating current systems, right here with real objects.
We have 4 stations today: the core room, the generator bay, a parts wall, and the control room. Let's move. This is a magic sound. A simple coil of wire, nothing special until current flows through it.
Watch what happens when I connect the battery. Did you see that flicker? That's not a defect. That's self-inductance. Here's what's happening. When current starts flowing through this coil, it creates a magnetic field around it. The changing field induces an EMF, an electromotive force, right back into the same coil.
And by Land's law, that induced EMF opposes the current that created it.
The formula is E prime equals negative L times delta I over delta T. L is the self-inductance, measured in henries. The negative sign is Lenz's law. It always fights the change.
Think of it like this. The coil doesn't want the current to change. When you turn it on, it resists rising. And when you turn it off, it resists falling. That's why the LED flickers.
Now what if I bring a second coil nearby? When the current in this coil changes, it induces an EMF in that one too. No wires between them, no contact, just a changing magnetic field traveling through a space. This is mutual inductance. The formula, epsilon sub 2 equals negative m times delta I1 over delta t, where m is the mutual inductance constant. This is the entire principle behind transformers. Your phone charger uses mutual inductance to step down 220 volts to 5 volts safely. Medical pacemakers use it to charge wirelessly. It's not magic, it's mutual inductance. So now, our director has more to show you. Let's go to the generator bay.
AC, DC. These two things look similar. Both produce light and movement. But the current inside them is completely different. In a DC circuit, like this flashlight, electrons flow in one direction. Steady, constant. That's direct current. But in an AC circuit like this fan, electron current reverses direction many times per second. In the Philippines, 60 times per second. That's 60 hertz. These electrons are literally going back and forth inside those wires right now.
The voltage in an AC source follow a sine wave. V equals V naught times sine of 2 pi feet. V naught is the peak voltage. In the Philippines, that's about 311 volts. But we quote it as 220 volts. Why? Because we use the root mean square value, or the RMS. The RMS voltage equals V naught divided by root 2, about 0.707 times the peak. This is the effective value, the equivalent DC voltage that will deliver the same power. That's why your appliances are rated at 220 volts and not 311 volts.
3 appliances share completely different voltage current relationships. Let's break them down. First, a lamp, a resistor, and AC. The voltage and current are in phase. They rise and fall together. No delay. Almost just like I equals V over R. Next, a fan. Inside is a motor, which acts as inductor, and AC the current lags the voltage by 90 degrees, means voltage leads, current follows 1/4 cycle behind. This happens because the inductor's back EMF opposes changes in current. Its opposition to AC is called inductive reactance. XL equals 2 pi FL, which means higher frequency means higher reactance. And in a pure inductor, average power is 0. Energy is stored in a magnetic field and returned. Finally, a charger. It contains a capacitor. In AC, the current leads the voltage by 90 degrees. It moves 1/4 cycle ahead. Its opposition is called capacitive reactance. XC is equals 1/2 pi FC, which means higher frequency means lower reactance. Like the inductor, average power is 0. Energy is stored, but in an electric field. So remember, a resistor, inductor, and capacitor. What happens if we combine the three?
Imagine a radio playing. Hear that? That's just not noise. That's what happens when you have a resistor, an inductor, and a capacitor all working together. An LRC circuit, and they're not yet in tune. In an LRC series circuit, all three elements are connected in a line. The same current flows through all of them. But here's the problem. Their voltages are all out of phase with each other. We can't just add them up like regular numbers. We need to use a phasor diagram.
Think of each voltage as an arrow rotating in a circle. The resistor's voltage is in phase with the current, so it points forward. The inductor's voltage leads by 90 degrees, it points up. The capacitor's lags by 90 degrees, it points down. Since the inductor and capacitor oppose each other, they partially
The
cancel.
total opposition to current is the impedance, Z, where Z is equals to the square root of R squared plus the quantity XL minus XC squared. The current RMS is just VRMS divided by Z, where the stronger the impedance, the smaller the current.
Now, watch what happens when the dial of a radio is adjusted. Now, watch what happens when the dial of a radio is adjusted. The capacitance inside the circuit is changing, and by that, XC also changes. At one specific frequency, XL equals XC. They cancel completely. The impedance drops to just R. The current is at maximum. This is resonance.
The resonant frequency is just F0 equals 1/2 pi times the square root of L times C. When turning this dial, we are literally tuning this circuit to match the broadcast frequency of a radio station, maximizing the current and pulling that signal out of the air.
When resistance is very small, this becomes a pure LC circuit. In a perfect LC circuit with no resistance, energy doesn't dissipate. It oscillates back and forth between the capacitor's electric field and the inductor's magnetic field over and over at the resonant frequency. This is LC oscillation, the heartbeat of every radio oscillator and TV tuner ever made.
The next time you tune a radio, charge your phone, or flip on a lamp, you're experiencing self-inductance, mutual inductance, AC circuits, and resonance all at once. That's the plan.
Let's take one last look at the plant. Over there, the coil room, where we learn that self-inductance makes a coil resist its own changing current. And mutual inductance lets two coils communicate without touching. Thus, the principle behind every transformer and wireless charger you've ever used. The generator bay, where we saw that AC reverses direction 60 times a second, creating a sinusoidal voltage. The 220 volts you use at home is the RMS value, which is the effective voltage. And an LR circuit controls how that current rises and falls with a time constant of tau equals the resistor over phase uses water. The inductor, current lags, stores energy in its magnetic field. And the capacitor, current leads, stores energy in its electric field. And the control room, where all three elements combine into an LRC circuit. Impedance Z controls the current, and at the resonant frequency, XL cancels XC and the current peaks. That's how a radio finds its station. And that's LC oscillation powering every oscillator in the world.
Thank you for visiting the plant. This has been our Physics 2 report on Lesson 7.2. Good shift, engineers!